Welcome to the IBU podcast, broadcasting from Sarajevo, Bosnia and Herzegovina, a platform proudly brought to you by the International Birch University. This episode in particular is brought to you by the Department of Electrical and Electronics Engineering. We are honored to welcome Dr. Engineer Mayukh Bhattacharyya, highly accomplished analog mixed-signal design engineer with over 6 years in the automotive semiconductor field, specializing in functional safety ICs and system-on-chip integration. As Vice Chair of IEEE Solid State Circuit Society Germany and a PhD in microelectronics, Dr. Bhattacharyya brings a wealth of expertise from his work at Continental ADC, TES Electronic Solutions, and Offenburg University of Applied Sciences. Mayukh, thank you for joining us. Welcome to Sarajevo.
Thank you very much for the invitation, and I'm looking forward to the discussion today. And before we start, I'd like to say two things. First, greetings from my colleagues at the IEEE Solid State Circuit Society Germany chapter. Our chair and secretary has sent warm greetings for all the audiences from their side. And secondly, I have to say, it's a lovely setup, and it is a beautiful city with excellent food and excellent drinks. And so I'm looking forward for my visit here. Thank you very much.
Certainly, the pleasure is ours. Now, Mayukh, would you please explain what semiconductors are and then extrapolate it, take us to the geopolitical context. Why are they important? Who are the key players? And what's currently going on in the world?
Thank you very much for the question. And as you said, recently, at least in the last 4 or 5 years specifically, we have seen a lot of discussions happening regarding semiconductor industry, around post-COVID times. And so I begin with the first part of your question, that is what is semiconductor? So as you can make out from the name, so semiconductor stands for something which is like a conductor. So as we know, traditionally, for example, metals, copper or aluminum or gold, silver, these are definitions of a proper conductor. And on the other hand, we have materials which are not regarded as conductors or non-conductors or insulators, as they are called, like wood, for example, this table is made of. So semiconductors are in between these two. That means in normal cases, they are not conducting, but if we can tweak the chemical properties of these materials by adding something known as impurities, so then they start behaving as a conductor. And that's why we call this kind of, not elements, but compositions as semiconductors. And then why the semiconductor is so important. In today's world, if you can see when we are sitting in this room itself, in a small area, all the electronic gadgets as we are seeing around us, the microphone, the cameras, laptops, our smartphones, our watches, even sometimes our glasses, and also the lights, they all have some sort of integrated circuits inside. And these integrated circuits are built by the semiconductors by putting a lot of small parts known as transistors, which are constructed by using semiconducting materials. So it can be pure silicon with some kind of impurities. It can be a compound like gallium arsenide, silicon germanium, silicon carbide. Depending on the applications and the requirements, we can produce in today's world different kind of semiconducting materials for different kind of applications. And the next and the more important part of the question is what is the importance of semiconductor in today's geopolitical scenario? So as you see, because the demand is so high, because we are surrounded by semiconducting materials for our day-to-day life. So it can be our cars, it can be our refrigerators, or even complicated applications like space, or say our aeroplanes or drones, satellites. So everywhere we need these semiconductors. So anybody who controls who has a control on the supply chain, on the equipments required for manufacturing these kind of semiconductors. So they are virtually in control of a large part of the economy. So they became the new oil. So semiconductors are regarded as a new oil globally.
That's a great phrase. Yeah.
Thank you very much. So as you can see in the past, also all the say like the competitions and the conflicts happened on the control of resources. So for example, if you go back in history, I was visiting Mexico, and then there I was like they were telling us about the Mayan civilizations and all kind of fights that happened between different Mayan kingdoms, and all the fights happened on the control of salt mines, because that was the key for that time, the key resource. So who controlled the salt mines controlled the economy. So all the conflicts were happening surrounding the salt mines. Later on, we have seen in the past 100 years a similar thing happening with the oil resources. And now we are in an era where we are seeing a similar competitive era coming just because of the control of these semiconductor resources. So it can be various kind of things which we can discuss in due course of our discussion. But that's it basically. So, and then you have see like the COVID has also exposed a large part of say a gap in the supply chain, because in the COVID times, for example, like in the automotive industries, the cars being manufactured, and they were like in the factory facility waiting for the chips to come to be fitted. But because of the corona and the disruption in the supply chain, things got delayed over sometimes 6 months, sometimes 1 year. And so that also exposed the vulnerability of the supply chain, the semiconductor supply chain that we have worldwide. And that's all the demand plus the post-COVID era, it all shaped the modern day semiconductor policies for each and every countries.
So you're saying semiconductors are absolutely critical for today's, let's say, geostrategic positionings of superpowers and very large influential countries.
It's not just only for sure for the superpowers and the large powers, because as I said, like it is that control that you have in a way on the economy, because as I said so far that these are essential for the most of the stuff that we're using today. So it's like a essential part of our day-to-day life, from medical field to like our cars to entertainments. We have the semiconductor chips are everywhere. So the control of the resources become essential for the control of the economy.
Let me ask you then, who controls the resource right now? Who is in possession of this precious resource?
Silicon is the most widely available element, say, worldwide. So that is actually very available. Like that's available very cheaply globally, I would say. But what happens after that is the key element here in the entire story. So like after you have the silicon, and to bring it to the level where we can use it for producing chips by using the transistors. So for that you need a lot of know-how, a lot of technology, and then finally finishing by a chip, an indicator chip, by using say a very advanced nodes technology, like today's world, like you have like sub 7 nanometer, 5 nanometer, 3 nanometer CMOS technologies. So to reach to that level, it's only very, very few countries are able to do that, because only few companies have the technology to do that.
What kind of technology is that, and why is it so special? I mean, it sounds like, and we've known that for a long time. I mean, it's a highly specialized, very expensive technology to sort of master and to install. But what exactly makes it so special and unique, so not many countries can actually start that production?
So the process of lithography is essential for the production of the chips. So all the lithography machines are the backbone for the manufacturing of the chips. So for the integrated circuits to be manufactured, we need something at the beginning called like mask layers. So masks are like stencils. So like for the imprint, to imprint the stuff, like so you need like a stencils. Similarly for production of the transistors and all the semiconductor parts, we need these masks. And these then by using the process of the lithography and the masks, we start building up all the layers in the chips, including the transistors and all of the passive devices. So that's why without a advanced lithography machine, you cannot manufacture these very small technology nodes that we have, like 3 nanometers or like below 7 nanometers. And that's why there is a company called ASML from Netherlands. They have mastered over the years this ability to manufacture the sub 7 nanometer chips by using very advanced form of lithography machine. It's called like EUV, extreme ultraviolet beams that they use, like 13.5 millimeter wavelength of lights that they use for the lithography process. And so all the foundries who are manufacturing these advanced ICs or advanced transistors below 7 nanometers, they mostly depend on the machines, the lithography machines from ASML worldwide. And at the moment, for the ASML to sell these lithography machines, they need permission from US government, then the Dutch government, and the Japanese. So without the 3 permissions, they are not able to sell the lithography machines to anybody. That means if anybody wants to manufacture chips with technology below 7 nanometer gate length, you cannot do it without these permissions of the ASML machines. Although, like, as we have heard, like there are some exceptions happening. There are like also sub 7 nanometer chips coming out from other countries without this machine, probably, but it's very difficult. So that's how, like, so if you see in the entire semiconductor supply chain, so if anybody controls this very basic but important niche area of technology, you control a large part of the supply chain.
How is that related to AI technology currently in operation?
Very good question, because a lot of modern and in the future AI chips will be constructed or will be designed by using these advanced node technologies. That means like 5 nanometers or 7 nanometers or even lower, like 2 nanometers. And without this lithography machine, you won't be able to make those AI chips. So that means in a way you are controlling the end product or the end user if you just control this one critical part of the supply chain.
Now the plot thickens, Mayukh. I'm sorry, I didn't mean to turn this into a geopolitical discussion.
No
but
problem.
It sounds like that. You know, you can't run away from that when you discuss semiconductors, chips, AI. It all seems to be integrated in the geopolitical competitive advantage of nations currently in operation. All right, very interesting. So, what's the role of? Let me put it this way: who are the main players in this industry right now? What's the role, let's say, of NVIDIA?
Okay, so before we start discussion on NVIDIA, so we have to understand again the ecosystem, the semiconductor ecosystem that we have. So in a semiconductor ecosystem, so there is like these companies, as I said, like ASML, for example, who provides you the machine, the lithography machine for the manufacturing of the chips. But then there are like different divisions, so different companies doing different activities. For example, like we start with the manufacturing of the chip. So the companies who manufacture the chips, then they are referred as foundries. So the examples are like TSMC, for example. Then you have like Samsung, S3E5 Microelectronics in Europe, global foundries. So they provide you with their own technology to design and manufacture the chips. Then are there like IDMs. So IDMs are like integrated device manufacturers. So they are the ones who, for example, design the chips mostly. And they can be also fabless. That means they don't manufacture the chips, but they can also have like their own fabs. So examples are like, as mentioned in your question, NVIDIA. So NVIDIA don't manufacture its own chip. It's a fabless, but it uses mostly the process from the TSMC, from Taiwan, to manufacture all their advanced chips, including their AI chips. And then also there are another important link in the supply chain. It's called like OSAT. So they are responsible for like packaging and also for testing. So like testing of the, when you do a mass production, so testing of the ICs are very important. So OSATs are responsible for like packaging, so putting everything together inside a packaging. So most like it could be plastic packaging or like ceramic packaging, depending on the application, and then testing and then releasing it. So these three are the key parts in the supply chain. And then of course, as I said in the beginning, the lithography machine is also, to my mind, is one of the key or essential players, because without that, nothing of this is possible. Yeah.
And how many machines are available throughout the world?
You mean like suppliers?
Lithographic machines.
Yeah, so the manufacturers I'm referring to, like, so I know like ASML from Holland. There is then one more company from Germany. They're doing it, and one more from Japan. So not very, very, very less people are doing this business. Yeah, and of course I have heard like also some companies coming up in China. Because of the restrictions at the moment. So, but you can count it in fingers that who can really produce specifically the advanced lithography machines are only very few.
Now, Mayukh, you mentioned Taiwan. What is the role of Taiwan? What's in it? What do they produce? What sort of chips do they produce?
So Taiwan you can consider as like the most essential geographical location at the moment for the complete semiconductor ecosystem, because they
so we're talking about the
ecosystem now, because they house the largest number of foundries concentration-wise. Taiwan is not a very big country, but they house, for example, like TSMC, the biggest foundry. Then they have like UMC. Also from there, so majority of the manufacturings of the semiconductors still happens in Taiwan. So the diversification have started, and that led to, for example, like if you have read recently, like all the countries, big countries, are having their own CHIPS Act. So US has its own CHIPS Act, so does the Europe and Japan, South Korea. So everybody saw the most critical link in this entire supply chain is Taiwan. So if something happens in Taiwan, then the complete supply chain is disrupted. And that's why a lot of the countries are pressing for local manufacturing of the bulk of the semiconductor products. And that's how these CHIPS Acts have come up globally. A lot of money has been allocated by each of these countries, and the aim is like you have most of the manufacturing happening within the same geographical location, or at least which they think that the safer geographical location in future. But at the moment, it's still pretty much dominated by Taiwan.
Is Germany following the suit?
Yes.
Yeah.
So there's like an EU CHIPS Act, and also like Germany is also trying and investing a lot for the semiconductor manufacturing. So for example, like Dresden in the states of Saxony, is known like Silicon Saxony, part of that. So they're having already some of the fabrication plants, and also planning some of the fabrication plants in the future. That's in the Europe. Then we have seen in the US, for example, like TSMC is opening its manufacturing facility in Arizona, Samsung in Texas, and probably a lot more going to come in US. So far, I think they are the one who has allocated maximum number of fund for these projects. Also recently, I was seeing, like, I think last week or a week before that, according to the new bill, anybody who is investing in the manufacturing of semiconductors in US will get 25% of tax discount. That means, like, if you are investing $1 billion, then $250 million gonna flow back, which I think is very lucrative at the moment. European chip sector also there, and they're also pushing, allocating a lot of funds for the same reason. As I said, for example, like in Germany, Switzerland is putting a lot of money in innovation, not much in production, but like in innovation, design, in R&D of these semiconductors, of advanced semiconductors for the future. And then you have, like in Japan, in South Korea. India is having also a plan to open its own foundries. I think it's 3 or 4. It's already planned. So I think next 5 to 10 years will be very, very competitive between all these countries. And of course, China has already a lot of its own manufacturing, and it's also producing pretty advanced node chips, at least what is available publicly. So globally, I think it is a very, very competitive time that we are getting into in the next 5 to 10 years' time.
Speaking of competition, R&D and innovation, what's the top innovation in the field? What is the trend, ongoing trend in the field of semiconductors now?
So the ongoing trend in terms of application, if you ask, so of course it's AI. Everybody's doing something with AI. Then you have an automotive, the field where I come from, the automotive semiconductors, a lot of new innovations happening. Again, a lot of, say, overlap between AI and the autonomous driving that we are seeing, so that's going to be the future. Mm-hmm. And companies like NVIDIA, Tesla, Qualcomm, they're investing heavily. There are also some other companies investing heavily in the automotive field, like in Germany, it's like traditional German companies like Bosch and Continental. Then you have, they're also like investing. For example, like we have a very good industry and industry like funded research happening in Germany. It's funded by Infineon. It's for like advanced computing for automotive applications. It's called like CECAS Mannheim. So like, which involve like 30 partners, including industrial partners. So like 90 million euros has been allocated for the next 3 years. So which is between, so it's initiated by Infineon, but there are also like industrial partners like Bosch, Continental, and then ZDF. And also university partners like TU Munich, Karlsruhe Institute of Technology, and Fraunhofer Institute, and so on. So as you can see, like, so a lot of investments and thoughts have been already given for in the advanced electronics for the future. Sorry, I got a bit digressed from the topic. So like, what also gonna come, I think, in the future in the time is quantum. Mm-hmm. So quantum computing, I see a lot of, it's mostly startups. So quantum computing is very much in the horizon, and I think in the next 5 to 10 years, a lot of commercial products gonna come in terms of quantum computing. It's still like more like R&D, and things are getting over there. Companies are trying to move towards more like industrial, large-scale industrial applications, I would say, and that's gonna come. And also quantum sensors. So there's also like, I think something that's gonna come in next 10 years, I'm pretty sure.
What are those? What are quantum sensors? For the audience, please explain.
Quantum sensors, so I'm not really an expert in quantum sensors. So we had really a nice webinar about a month back from a Professor Jens Anders from University of Stuttgart. And he presented there in details about the quantum sensors. But in a nutshell, they can be used for different kind of applications. It can be like medical applications, medical sensorics, or like even automotive applications. See, at the moment, it's still in the development. Also, price-wise, they're not so competitive to the CMOS counterpart, but it's something that's going to happen in the future, maybe in 10 years. So when the price reduction happens, probably, and then they will be like more useful, I guess, or more attractive for the large-scale industrial applications. And also in terms of technology, for example, like we are still like heavily relying on the CMOS, so the complementary metal oxide semiconductor technologies, and so they were like, initially it was mostly like planar CMOS, and then we have like fully depleted CMOS structures, then we have like FinFETs, and slowly also there is a trend to look beyond CMOS because of the scaling, because you have a limitation regarding how small you can go. Like you are already like 3 nanometers, 2 nanometers, so max is like 1 nanometer, and then that's the end of scaling for CMOS. So then there is also a lot of researches happening to look for other kind of technologies, for example, like carbon nanotubes or graphene technologies, then organic transistors, then they're like printed or flexible technologies, they're also coming in. So those things, they are still like more in the R&D and less, and not so much for the large-scale industrial applications. But probably in next 10, if not 10, I guess 15 years, we will see a lot of these technologies coming also into large-scale industrial applications. Then we have...
Why do you think, let's say, 10 or 15 years is required from a R&D phase to transition to a commercial phase? What happens in between?
Yeah, because I think it is two things. Because in R&D, it's a very controlled environment. So I give you some example, like in terms of application, like because I come from automotive semiconductor background, so in automotive semiconductor has one of the stringent quality control. So we have, you will be surprised, I was talking with some of the guys even from suppliers who supplies to like say defense manufacturers or to the or like other kind of industrial manufacturers, and everybody were like saying like why automotive is so strict. Because we follow something known as like a SEAL D level of safety, functional safety requirements. So
please explain what it is.
Yeah, so it is in general, it is like one of the highest form of safety. So like, so you have, so if you, so just to explain, it's like if you design something, it has to have enough number of backups. So in case things goes wrong, something fails, if it still fail in a safe mode. Why? Because you are driving a car which has a braking system which is controlled by an IC. So in case your IC fails, this integrated circuits controlling your braking system fails, then it has to fail in a way still your brake doesn't fail. Otherwise we are talking of a catastrophic situation. And it is everywhere. So it can be like an airbag, it can be any kind of, say, safety measures, like even your steering control has a chip. So all of these have to have a system, a backup system in the design itself, so that not everything is failing at the same time. So you have like a lot of, I'm not going into the design details, but we have like a lot of like backups or parallel paths in the design for this protection. So so that's what defined in the SLD requirements, which is the highest safety requirements for the automotive ICs. So to your question, like why, for example, it takes 10 to 15 years for a technology from R&D to go to the industry, because to reach this level of maturity, because you can produce something at a very controlled environment in the lab, and it functions, but it is a controlled environment. So maybe it's operating under a very controlled temperature and humidity and everything. But when it goes, for example, like a harsh condition, like automotive, the conditions are very harsh. So the temperature could be from -40 to plus 175 degrees Celsius. That's the junction temperature. Ambient could be like till 150 degrees Celsius. and also the environment in which these things are operating are very harsh. So to qualify a technology for this kind of robust and harsh conditions, you need that time to like tweak your process and make it mature enough so that you can produce it for a mass production without any large variations over the period, and a very robust solution in the end. That's why you need this time of this long process of development and qualification over the years till you reach that level of maturity. For example, in automotive, in a lot of applications, we don't always quite go for very advanced nodes. It depends on the application, but we go with mature nodes because we know these are like process used over the years, developed and being considered as stable. So we use, so our focus at the beginning is always on the robustness of the process of the technology.
So are you saying that 10 years is required, let's say 10 years, for a new technology to be introduced into a new car?
I think minimum, yeah.
Minimum.
Even for your record, if you see a standard life cycle of a chip development for the automotive applications, it is standard is like between 3 to 5 years. So if you start today, so from next 3 to 5 years, you can have a commercially viable chip that you can sell in the market.
I think that's very important, how you put it, for the general public to know that innovation doesn't happen in a vacuum, and it's not rolled out in the marketplace immediately.
Yep.
There's a very, as you explained, a very controlled and stringent process of verification of technology, validation of technology, before it's introduced into commercial operation.
Yeah.
And the same goes for vaccines. In the biotech industry, decades are required to develop an operational vaccine and so on. So it's not something, including the COVID-19 vaccines and so on, it's not something that takes place in a week's time and gets rolled out in the marketplace. So that's very important that you explain that to us. And also, I'm just thinking, we've had a great interview with Nami Hello, IBM Germany, and he explained to us how quantum, his team is developing quantum computer in Germany, and he explained to us the extent to which this technology is advanced and the operations behind the scenes. So it was a fascinating interview, by the way, and I suggest to all viewers to go back and see that. And now I'd like to, since you mentioned auto industry in Germany, please tell us a little bit about your background. What's your expertise? What do you do on a daily basis? And what's interesting right now? What's hot in your industry?
Thanks for the question. So my background, as you introduced me very nicely in the beginning, so I did my bachelor's in electrical and electronics engineering, and then master's in communication media engineering, and finally my PhD in microelectronics from the University of Freiburg. So my research area during my PhD time was mostly like ultra low power sensor systems. So I designed a system on chip for passive biotelemetry applications. So it's like for bioimplants. It can be, for example, like measurement of pressure, but inside blood pressure, but inside the body. And it has no battery. It can work with externally by using an RFID reader, or like your smartphone with an NFC reader. So most of our smartphones, they come these days with an NFC reader or a tablet. So you can use that to interact with the implants, and you can use the same reader or device also to power. So when you take away the device, it becomes lifeless and it has no battery, so it doesn't cause any harm to your body. So that was my research areas during my PhD, and for the last 6 years I'm working in the automotive semiconductor company. And so
what are you working on, if it's not a secret?
Just like different kind of automotive semiconductor chips, like most like functional safety chips. So nothing in specific I want to mention here. Yeah, so where I work is a pretty like big MNC company, very, very famous for producing state-of-the-art semiconductor ICs, automotive applications, I will say. And that is my current engagement. And since past year, I'm also like the vice chair for IEEE solid-state circuits Germany section. So I'm again trying to come back a bit and keep in touch with the academia, with the academical research. Just also, it's given me a lot of pleasure actually to also interact with the academia and to see like what's happening in the, also like researchers, that what's happening in the academics. As we discussed so far, that a lot of things that are gonna come in the future is still actually the R&D is happening in the academics. So yeah, so that's my background in general. Yeah.
That's your background. Is there anything in particular that's fascinating right now in your industry that perhaps you're working on?
So in general, I can say like what's happening in the autonomous automotive semiconductors. So it's like autonomous driving, for example. So for autonomous driving, you need also different kind of sensor fusions. That is very interesting. That's happening. So like, so if you make this interview like 7-8 years back, there was something was very hot topic. It's called like LiDAR, L-I-D-A-R. So like radar, you have LiDAR. And so like everybody was saying like, oh, LiDAR is the future and we will only gonna have LiDAR, and everybody invested heavily in LiDAR, but people realized soon like its limitations, and also price-wise it was not very competitive. And then the focus shifted to radar. But now again, due to again scaling and better understanding of the technology and mass production, there is a trend that LiDAR is making a comeback, and because the prices has reduced compared to earlier. So in future, I think it will be a lot of this data fusion happening between different sensors for like autonomous driving. So like it can be like a fusion with the LiDAR, radar, and cameras. And a lot of companies like, for example, like Tesla, they're working on it. I think NVIDIA also has something in this direction. So this is in terms of automotive semiconductors. Also, then again, the use of AI. Then very interesting use of AI models are coming up. So like this year I was in San Francisco for the IEEE Solid-State Circuits conference. And I was very lucky to see a presentation by Professor Daniela Rus from MIT. And she showed us how they're developing AI models from, if I'm not mistaken, from they study a worm, I guess. And from that worm, how it, said, they use the worms to select the control systems to develop their AI models. And based on that, she made some presentation like how it improved. So like it need not has to be like this generalized AI model, but like application-specific AI model that research groups are developing that will be very key, for example, for autonomous driving in future. Then you have also in general the architecture of the cars are changing. For example, like at the moment, you have lots of ECUs we call like electronic control units. So the modern approach or the future approach is to reduce the number of ECUs and to have like one centralized sort of brain for the whole car, which controls then the different sensors. And then also like to have these AI chips located very close to the different sensors so that the data is already processed locally. Large part of the data is locally processed and then given back to this main controls unit to reduce the latency. So this is what happening, like a very beautiful fusion between like AI and the automotive applications. And then also another challenge in the automotive is in the car is like cars traditionally have a large number of cables running around. If you see ever your car in the servicing, you will see like so many cables running around the whole cars. I think somebody told me like it's around 21 kilometers of length. The car is typically like 5 meter length, but it's like 21 kilometers of length of wiring that goes around. So the future idea is to get rid of most of the wires and to use wireless communication inside the car, like Ethernet, for different kind of activities. So, but it's still like work in progress. A lot of like investments already been done. Companies are moving slowly in this direction. Yeah, but these are like basically what's going to happen, I guess, in the next 5 years.
That means that the R&D department is 10 years ahead of all of us, essentially, in the car industry. Yeah?
In the R&D, yes, but that's how it is. Like if you look back, what we are using now, it's like, for example, like AI, what we're using now, it was already in work in progress in the last 10, 15 years, or even longer, I would say. Yeah.
So essentially the industry is 10 years ahead of us, ahead of commercial application, essentially.
Yeah.
That's good to know.
That's always in the history. Like if you see all the modern technology that we say we use, a lot of them were actually founded much earlier for like different applications. But as I say, like you have to find also commercial aspect of the technology, and that takes time.
That takes time. It's good. The reason I'm mentioning this is the fact is you know that the R&D departments have already advanced to a very significant stage, and now they're gradually releasing that technology into the marketplace. So
yeah,
gradually.
It's as I say, like it has to be like when you going for the commercial product, like you mentioned about the vaccine. So even when you design, for example, something for the medical field, an implant, it can also be like it's a pacemaker or something. So the qualification process is pretty long and stringent, and that takes time. So you can develop something, but to bring it to that level of maturity where you can really have a commercial product, it is always takes time.
Takes time.
Yeah.
And safety sort of is the most important
framework
that gets calculated in. All right. Now, Mayukh, tell us about IEEE, your sort of motivation to join and to take on that leadership role. How did that come about? What happened there?
So IEEE is like, so IEEE stands for like Institute for Electrical and Electronics Engineering. So it was like, so founded like 1963 by combining two separate set of societies in its United States. So at the moment it's like it's in New Jersey is the head office of the IEEE. So and since then IEEE had grown in leaps and bounds. So for example, at the moment they are present in 160 plus countries and more than 400,000 members. It's a big, very, very big. I think it's the largest organization. And for my motivation, so I was, since my study days, so the universities, through the universities, you have access to these, to IEEE, to the different magazines, to different conferences, papers. So then you are like already introduced into the world of IEEE and what you can do it. And then when I was provided with the opportunity to contribute actively for the research community in Germany, then I took the opportunity to join as the vice chair for the IEEE Solid-State Circuit Society. And yeah, that's my motivation. So it's a way of like give back to the research community, because I used once it as a student, also as a PhD student, and it's for me as a professional, it's my way of giving back or connecting back to the research community.
What is your role as a vice chair? What do you do on a daily basis?
So vice chair is technically has actually all the responsibilities that the chair has. So in absence of chair, so I take the lead role. But in our case, we are really like, we work very, very closely. So the chair is Dr. Mustafa Navito from International University in Stuttgart. So he's our chair, but and we have also another fantastic colleague from the University of Passau, Nikolaus. He is doing his postdoc and habilitation over there, and he's our secretary. So three of us, we are very closely bonded, and we share a lot of responsibilities, so we don't really have this, between us, this demarcation that who does what. And so giving a bit of background of these chairs, so this chapter was kind of dormant for the last 25 years. And then after our election in 2024, we bring a new life and new energy to this chapter activities. And since then, we have done a lot of webinars, inviting professionals and professors from universities and industry to present latest state-of-the-art activities. Then we facilitate also distinguished lectures. So IEEE has a list of distinguished lecturers. So they are invited then, for example, like in universities to give their lectures. So we facilitate that. Now we are planning also an industrial event with one of our top semiconductor company from Europe. That's probably gonna happen in November, end of November, that we have planned. And then also we try to cooperate with other chairs. For example, like we have, last year we tried to cooperate with, from the IEEE group from Tunisia. And also my colleague Mustafa, I know he is involved in promoting semiconductors, the interest in semiconductor technologies among students in school. So he does that, like to encourage more and more young people to join, to become like the future of the semiconductor industry, because we see like we need more and more people. We have like, as we were discussing today with the dean of your university, that everywhere we see the same trend, like not so many people for the study of electrical engineering and specifically for microelectronics. So it's very important that you bring this message to the young people and motivate them so that we have enough people in the future carrying on the baton of microelectronics.
Sounds exciting to me. Are there any opportunities for collaboration and cooperation between Bosnia and Herzegovina, institutions in Bosnia and Herzegovina and IEEE in Germany? Is that how it works? Or?
So we always look for chapter collaborations with the chapters from other geographical locations. So I see a big possibility, which we can discuss in future, how to cooperate and increase our engagement between these two chapters. And we can also try to, for example, like facilitate cooperation between different universities in Germany and with Bosch for collaborations like R&D collaborations in future. Then you have also like possibility, for example, under EU CHIPS Act also to join this kind of economic collaborations. So in short, yes, it's possible.
Well, it's very good to know that, because it's very important to sort of initiate exchange of ideas of people, some sort of mobility, you know, in this professional sense, that can lead to you know, significant innovation in the field, I guess, and sort of through those collaborations. Now, what does IEEE, how does IEEE function in the sense, is this specifically an organization that deals with itself, if I should put it that way, or are there any significant collaborations with industry professionals, with the companies operating in the market, or how does it work?
So IEEE it's like an organization that mostly for the professionals and students. So it doesn't directly help in any kind of collaboration that you're referring to, but what it provides you a platform for professionals So for example, like you have different kind of conferences and journals that you can be a part of, or you can, for example, through the IEEE digital library called Explore, you can, if you're a member, then you have access to those top quality conferences and journal papers for your own work or research. Then you have the possibility also, for example, like networking. So there is something called like IEEE Collaboratech. So in IEEE Collaboratech, you can also network with other of your peers, or somebody you want to get in touch with something specific in your field. It could be like somebody from completely different country, or different universities or companies. So you can do that through IEEE Collaboratech. You can also do something known as like enroll yourself for like mentoring. So if you're experienced professionals, you can be mentor to somebody. On the other hand, if you are a young professional, you can look for a mentor as a guide from your field, a professional, maybe 20, 25 years experience, you ask for guidance. So there are also those kind of possibilities. And there are a lot of like professional trainings happening all the time. For example, like it could be anything about this advanced circuitry design or like advanced nodes, or it could be even something simple like how to write a peer-reviewed journal paper. I have seen that as well. So there are always these kind of trainings available. I will say at a very reasonable price if you're a member. So these are basically the activities that IEEE get into. Yeah.
So what's your recommendation both for academic staff and students? What do you recommend to academic staff? How should they get involved at the international level?
I think academic staff first, okay, of course you need a membership, or normally I think you can have a membership as the university. Then you can have like access to everything. And and then secondly is of course to take part more actively. For example, like if you can form, if you want to form, say like something cooperation with the other chairs within the IEEE, or like organizing conferences, for example, you can, there is a process to do that, so you can go to that process, and if IEEE accepts it, your proposal, then you can also organize IEEE conferences. Then, of course, get involved in publication. If you are like doing state-of-the-art work, then get involved into presenting in the conferences and journal papers. It's same for the PhD students, for example. So you can also, you should actually try to publish your work in peer-reviewed journal papers and conferences. And for example, like in IEEE, if there are like possibilities of getting like a student grant for travel in some conferences. So there are a lot of benefits that you can have being a member and or for publishing in IEEE.
Is there anything else we should know about IEEE from your point of view? Some sort of advantage, something that we should all know about?
Advantage, yeah, as I said, like, so the main idea of IEEE is to provide that platform for professionals, or it can be both experienced or a young professional. So if you want to connect and see what's happening in the latest in the industry or the academia of a certain quality, so I think IEEE provides that for sure. It has a very good set of journal papers, which very high quality peer-reviewed journal papers. Then they have also very good quality conferences, which you can visit, for example, just to see what other people are doing at the top universities as well as at the industry. So, for example, like in IEEE Solid-State Circuits Conference, you have participation from the universities worldwide, but you also have participation of industries. They're like stalls from different industrial partners who come and present their latest things that they are offering.
So is there a collaboration between industry and IEEE at any level? Okay, that's a conference level.
There, yeah, so there's very like, I think,
projects, mutual projects.
I'm not really aware of that. I cannot say that, but I think it happens maybe at very like, mostly what I've seen, it happens at like between universities and industries. that's or like universities, industries, and research institutes. But something really like a large project initiated by IEEE, I'm not aware of, so I cannot say that.
Right. Now, I have to say that Mayukh, you inspired me to perhaps even join IEEE, although I'm not, you know, an expert in the field, but it sounds very informative, and particularly it's interesting to me from the standpoint of networking and getting in touch with leading experts in the field, and you know, getting to learn all about the innovation that's currently taking place.
Yep.
It's fantastic. Sounds fantastic to me. So I'll have to look into it. All right.
But just before you finish, so there is actually different kind of societies in IEEE. Yeah. So it's not like only solid-state circuit society. There is even societies that only deal, for example, like with, say, automation, industrial automation. They're like also same thing with the information technology. So you may not be like connected to the solid-state circuit society, but maybe you are, for example, you find more connection with something to do with the data science or information technology. So the area of expertise that IEEE offers in terms of the societies is quite wide. So maybe you find something there.
Certainly something to think about. Now, I was going to ask you rapid fire questions, Mayukh. Are you ready?
Yep.
Okay. Now, I'll ask you 4 questions, and you just answer, you know, one or the other, essentially. So, online or in-person conferences?
In person.
Industry collaboration or academic research?
At the moment, industry cooperation. Yeah.
Cutting-edge research or practical application?
Applied research.
IEEE student membership or professional membership?
If I can, student membership, but I can't, so I will stick with the professional membership.
That's a good one, like that. All right. Now, Mike, for students watching, you know, students who are just starting their career, professional career, in engineering or tech, what's your key piece of advice for them? What do you suggest to them?
So, like in general, or like
for success? For success.
Okay, so in general, if you're starting now, it's a very like interesting and challenging time, because the technology is changing so fast. So like whatever was like really state of the art 5 years back may not be like completely like state of the art trained at the moment. So that means if you are like starting a career, keep learning. That's very important. And because I am from the chip designing background, and I want more and more young people to join chip designing. So for those bunch of people, I will say like it's a very exciting field. It's absolutely fascinating. Once you get like into this world, you will get addicted. Because when you design something with nanometer length, and you put them together inside a chip, and you turn it on everything the first day of the chip, and it works, there is no feeling in the world that can replace that. It's the best feeling. No money, nothing can buy it. So it's a great field. Come and learn chip designing. It doesn't matter analog or digital. It's because you can see like you need it everywhere. So the applications are like endless. And it's a lot of scope of innovation still available, even in the future. And second thing is like, because we are in the age of AI, it's a lot of, even the AI is coming into picture, for example, like in designing of the chip itself. And a lot of R&Ds are happening. For example, in Princeton, if I'm not wrong, a professor is working on it, I've seen recently, on use of AI itself in the designing of the chip. But having said that, it's still, there is a huge scope and possibility for designers themselves to learn and do stuff on their own, even in the coming future. Doesn't matter AI comes or not, it's still a huge possibilities that's left. And lastly, again I repeat, it's for all of us, it's valid. Like you're a young professional or a professional with experience, we got to keep learning. There's no end to it. Because every day I see new things are coming up, so you have to learn, that's it.
So the message is keep learning.
Keep learning, keep yourself updated, upgrade your skills, and that's how you're going to survive.
Thank you, Dr. Bhattacharya. This has been very motivational, and both motivational and informative.
Thank you very much. Thanks for the invitation once again, and I have seen your podcast in the past and really liked it, and I will tell and appeal to all of your viewers and listeners to subscribe and listen to your podcasts now and also in the future, and looking forward for further interactions.
Well, that's fantastic. I was going to say that. I was going to encourage our viewers, to do that, but you already said it. So, and before we close, can students get in touch with you? Should they want to? Sure. Can they pop you an email, send you an email, and say? Yeah,
or in my LinkedIn profile. So
your LinkedIn profile.
Yes. That will be.
That's another, great, piece of advice for young professionals to get involved, to get networked.
Very important.
Very important. Fantastic. Thank you so much.
Thank you very
and
much.
We'll certainly have you on when you come back to Sarajevo. I'm sure you'll be coming to Sarajevo the following month. So we'll keep an eye on you. Thank you so much.
Thank you very much. Thanks for the time.
And that's a wrap on our conversation, which has been very interesting, very, very informative as well. Please subscribe to our video podcasts on YouTube, Spotify and Apple Podcasts. This particular episode, let me just remind you, this particular episode is a production of International Birch University, our Department of Electrical and Electronics Engineering. Thank you for watching.